Okay, so our last little topic is about bond enthalpy, and this actually belongs at the end of chapter 8, but it wasn't required for any part of the Vesper experiment, so I pushed it back a little bit. Basically, bond enthalpy is one way of calculating a delta H when you don't have it listed in the appendix. So some of us, while we were working on our chapter 5 project, had a hard time finding a delta H for a given chemical. And so one way to get around that is to use an estimate. It's a very rough estimate, but it's the best we have. And you're still going to use Hess's law in a way, all right? And so basically we need to do Lewis dot structures of everything, reactants and products. And then you're going to subtract, you add all the bonds broken together. So the values are on the next slide. I'll show it to you. Add all the bonds broken, and then subtract the sum of all the bonds formed. And whatever that difference is a delta H of reaction, estimated. Okay? So, as an example, I want to look at a simple combustion. So we'll look at CH4 gas plus oxygen. And of course, that's a combustion, so we would expect to get CO2 and water. Then I just have to balance it. You should be able to do that by now, so go ahead and pause it and work your way through it. And I wrote gas here, of course, because it's hot, it's on fire. So the next thing to do is to draw your Lewis dot structures. And so here I have CH4, which we have studied a couple of times. It looks like this. It's tetrahedral, so the molecule is nonpolar. Then I have oxygen. I have two of those actually, but each oxygen will have a double bond according to both Lewis dot structures and MO theory. CO2 we've seen a number of times. It looks like this. Double bonds on both sides. And then water, of course, looks like this, and I have two of those. That's two dots up there on the top. Okay, so we have these atoms connected to each other in these ways. And so what we're going to do is add up, again, we look at bonds broken minus bonds formed. So what I like to do is once I draw these structures, I'm going to remind myself there's two of those and there's two of this one. But all the reactant bonds get broken. This isn't true in reality, but it's the easiest way to manage this, and it will compensate for that assumption later when we add them all together. So we're going to break all the CH bonds. There's 4 CH bonds. We're going to break all the O double bond O bonds. There's 2 of those. So that's what we're breaking. We're forming 2 C double bond O's because there's 1 on each CO2. So 2 C double bond O bonds. We're also forming 4 total HO bonds because we have 2 waters and each water has 2 of those. So those are single bonds. So then I'm going to come over to this list here and I'm going to look them up. So CH is 413. That's kilojoules per mole. Ignore this 2 here. The O double bond O, the multiple bonds are at the bottom of this list. That's worth 495, but I have 2 of those. All right, so then we sum them all up. I would do the multiplication and then add 413. Similarly over here, 2 C double bond O's are going to be worth 799 each. So it's going to be 2 times 799. And we have 4 HOs, which are up here, 463. So our delta H of the reaction is going to be the sum of all of the broken ones minus the sum of all the formed ones. Oh, here we go. This is 413 times 4. So I have 4 of those bonds. 2, 2, 4. Okay, there. So we just go 4 times 413, which is 1,652, plus 495 times 2 in parentheses. So the broken bonds end up costing, and that's costing, it always costs energy, it's always a positive value, 2,642 kilojoules per mole to break all of those. And to reform, so we get this energy back, three thousand four hundred and 3,450 kilojoules per mole is formed. So to find our rough estimate, we will go broken minus formed. So we end up with an answer for this particular reaction of negative 808 kilojoules per mole as our estimate. All right. So again, a couple of key takeaways. It matters whether you have doubles or singles or triple bonds, so organize them. It matters how many total you have. If you skip the step of writing the Lewis structures, most people will forget how many bonds are in there. So write it out really neatly. Keep track of what is being broken. That's everything on the reactant side. And whatever's being formed, everything on the product side. And then you can plug them in, broken minus formed. This is a little bit of a different approach from what we did in chapter 5, where we would take products minus reactants. Okay, so it's a different approach. It is an estimated value, not a measurement, but we can at least tell that this combustion will be exothermic, which means it can happen. So that's a good place to start. Okay. So again, you can use that chart whenever you don't know, whenever you can't find a delta H of reaction from the tables or from the NIST webbook. The question might say calculate the delta H of reaction based on bond enthalpy, then you have to use a table like that rather than the delta HFs listed in the appendix.